My pleasure to introduce Kristian Bjerklöv, who's going to talk about dynamics of two quasi-periodically perturbed systems.
Okay, thank you. So first of all, I would like to thank the organizer for the invitation to this nice workshop. So I will talk about dynamics of two different quasi-periodic forced systems, and I want to kind of show that there are similarities in them, and there are things which may be kind of there are some general things which one can see in these models. So I will begin with the quasi-periodically forced quadratic map, and then I will say some results about the quasi-periodic Schrödinger cocycle and show that there are similarities in these models. So let me begin with the quasi-periodically forced. Do I write too small? No? Quadratic map. So we all probably know this one-dimensional map, which has been studied a lot in dynamics. So it's a quadratic map on the interval 0 to 1, and C is some parameters between 0 and 4. And then you want to understand the dynamics of this. And for the last 20 years, I mean, now we have a very good understanding of the dynamics of this map. For example, if I take C to be equal to 4, then this F is chaotic. So now one can imagine that we iterate this map, but instead of having a this constant fixed, we can let it vary with time. So we can look at a skew product map in the following way. So let us say that in the x coordinate, we take C of theta n x n 1 minus xn. So I have the same map as here, but I let the coefficient change with time, and the time, so the forcing is induced by another dynamical system, which is independent of x. So this is the skew product map. And the example I wanted to, or the model I want to investigate is the following one. So let me first stress that, okay, so it's the dynamic if this is a constant is very complicated. So of course this can be extremely complicated. We are far from a kind of a complete theory for this. So I just wanted to show one example what can happen when this happens, when we have such a forcing. So in this model I will take this base dynamics to be an irrational rotation. So let us say that T of theta is theta plus omega on the circle T, which is just R modulo the integers. And then I will perturb a map from this class F, which has very simple dynamics. So the somehow unperturbed map will be the following one, is f of x is equal to 3 over 2 x 1 minus x. So it's a member of this family. And for this choice of the value C, it looks something like this. And so this is y equals to x, and it has 1 over 3 is an attracting fixed point, and 0 is a repelling fixed point. And you can see that for this map, the iterate tends all to 1/3 for all x belonging to 0, 1. So starting with any point, they are attracted to 1/3. And now the idea is to, okay, so this is a very robust thing. So you have to kick it if you want to get some interesting dynamics. So we have to kick quite hard to do something, to kick it out from this stability. So let me also just say here that x equal to 0 is a repelling fixed point. So that you know that. So let's make some strong quasi-periodic kicks So I let this function c of theta, so I have defined this map. Now I will define how the interaction between the dynamics work. So I define c of theta to be the following. It is 3/2, right, plus 5/2, and then comes the formula here, which is not important, the actual expression, but I write it anyway. So it's 1 plus lambda cosine 2 pi theta minus alpha half minus cosine pi alpha and then this squared. So what is this? Well, we should there are two parameters. So lambda here we should think as being very large, and alpha, which appears here, it will be something which we vary. It will be a parameter. So lambda is large. And what does this look like? It looks something like this. Here we have 0. Here we have alpha. So it's close to 3/2 for most theta. And then it makes two bumps like this. And they go up to 4. And remember, for 4, this was in the more chaotic region. So by taking lambda large, you can make this very thin. The peaks are very sharp. And then by varying alpha, I can change the location of the peak.
What is on the horizontal line?
The horizontal line, it is theta. So it's just this. I just draw this function. So this is this function c of theta. Okay. So I can stress immediately that you can take any. It doesn't have to be this expression. It has to have this property with these peaks. And then it is one periodic. Sorry. So I was just drawing it on. Yeah. So it is one periodic. So let us. It's just that 1 is at 0. So let us do this from 1/2 to -1/2 maybe.
Det är just alfa ämnet för mig.
Yeah. So let us give a name for this map. So let phi be the following map. So it's a map from t cross the interval 0, 1 to itself. And then I just define it like this. So phi of theta in x is just theta plus omega. And then this c theta x 1 minus x. And then we have the obvious notation. It is that theta n x n is the nth iterate of a point theta n x. And now we want to understand the dynamics of this. So what can happen? And the kind of idea why this could create something strange, some complicated dynamics, is the following. So if I look at theta nx, then we can think that for most of the thetas, this is close to 3/2. So for most of the time, the system wants to get to 1/3 in the x direction. But then we kick it out, and then it will go back maybe to this 1/3, and then we kick. And the idea is something like this, that close to 0, let's say that we come with an iterate which is close to 1/3, then the first kick, which happens at 0, the idea is to kind of, that this 1/3 could be mapped up to 1/2, and then 1/2 with the second kick could get up to 1, and then at 1 it's mapped, well, it's the same as mapping 0. So you see, so 1 is mapped down to 0, and once you get down to 0, or say close to 1, close to 0, then you are close, very close to the repelling fixed point, and then you get stuck there. So you could kind of kick this into something which becomes unstable, or at least less stable than it was. So that's why we need these two kicks. So one kicking it up to 1/2 so that we can go up to 1. So let us put some assumptions on the omega here. So let us assume that omega is Diophantine. I don't define it as it's a full measure set of omegas. And then let me state some of the results. So the first theorem, which I proved some time ago, is the following, that for any lambda sufficiently large, remember lambda was this kind of making this very thin, the peaks. So for any lambda, you can find an alpha, so you can fine tune this, you can move this alpha such that the following holds. And you can get the following, that there exists a measurable function psi from t to 0, 1, such that it's the graph is phi invariant, meaning that theta of theta, phi of theta, psi of theta is equal to theta plus omega psi of theta plus omega for almost every theta. So it means that we have some graph which is invariant. So if I start on it, you sit on it forever. And it is attracting, so xn minus psi of theta n goes to 0 exponentially fast for almost every theta in t and all x in 0, 1. So this means that for almost any theta, we start with a theta, then any point in the fiber will get attracted to this graph when you iterate. So it is an attractor. So when you iterate, of course you have rotation in this direction, but then you get closer to this, and they go exponentially fast. And then the thing is that the infimum of xn for n greater or equal to 0 is equal to 0 for almost every theta and all x equal to 0. So it means that for almost any theta, any x you take will come arbitrarily close to 0. For example, I could take a point on the graph, and the graph will be arbitrarily close to 0. Since the graph, if it was equal to 0, it would sit there, and since we have this rotation, it's invariant. Well, so this graph cannot be continuous. It's highly discontinuous. So this is an example of something called a strange non-chaotic attractor. So it's strange in sense of geometry, but it's not chaotic, because in the fiber direction we have a negative Lyapunov exponent, and in the base dynamics we have 0 Lyapunov exponent. So this is one called this strange non-chaotic attractor. So the graph x equal to psi of theta is an example of an SNA. So there is lots of kind of numerical papers about this, the existence of this, but very few kind of rigorous results that they do really exist. And then one could ask, what is the kind of the geometry of this fractal or this graph? So there is another theorem So let lambda and alpha be as in this theorem. Then there exists a closed set of the following form. So A is the set of theta and x such that theta is in the circle and 0 and x is between x and x is between 0 and a function h of x, where h of x, or let's say like this, h is a function to 1/3 1 is continuous. So it means that we have some kind of graph which is close, well, it actually looks something like this, the graph. Approximately like this. So we have, so A is this closed set, so everything below the graph of this function. And in fact, such that the omega limit set of almost any point is this. For almost any theta in t and all x in 0, 1. So the omega limit set of almost any point goes into this. So you will be everywhere here. So in some sense, if you take the graph here, now it's only a measurable function, so it doesn't. But if you take the closure of it, you have a two-dimensional object. So this is attractive in the sense of Milnor.
I'm sorry. What is an omega limit point?
So you take the orbit of this theta x n. Where did I have it? Yeah, here. So you take the orbit. So for n, you look at this set, and you take all the limit points for it. So it means that if you take a point, almost any point, it will become arbitrarily close to any point in this set. So it will be everywhere. And then one can ask, how is this? How are they created, these kind of sets? So to do this, let me do the following. So we can ask about the creation of this attractor, because there are some kind of universal scaling limits which seem to exist, and I want to stress them also in the Schrödinger cocycle, that you have similar asymptotics. So let now alpha and lambda be as above. So we fix lambda sufficiently large, and when you fine-tune the alpha, and then we do the following. We let theta of beta be the following thing. So we take theta plus omega, and we put a beta in front of this. Where beta will be a new parameter, which is between 0 and 1. So when beta is equal to 1, we have this map, which is in this theorem. So then we have this attractor. And then when we make beta smaller, we kind of lower the height of this. So we can change the strength by this parameter. And we want to see what happens with this set, with this curve. And then there is a theorem. So my student, Thomas Olsson Timodas, he has investigated this, and there seem to be kind of some universal scaling limits. So there are scaling limits which has appeared in numerical estimation, but there have been no kind of rigorous proofs. But now we can really show how they are created, these sets. So this is a theorem by him. So this is Olsson Timodas. So it just appeared on the archive, this paper. And he shows the following thing, that we take this beta strictly smaller than 1. So then there exists another of these invariant graphs. But now it's C infinity. So immediately you drop it, you get C infinity. And the graph is invariant. So the graph x is equal to psi beta of theta is phi invariant, meaning this, that you have it for all theta. So. And again you have that xn minus psi beta theta n goes to 0 exponentially fast. So
Phi or phi beta?
it should be
Phi
it should be this phi beta. Thank you. Yes. So as soon as we make this, you have the C infinity curve, and then what he has looked at that. Okay, so now we have a C infinity curve, which lies. So it means that it will be strict. Well, no, I don't draw it as it looks like. It's much worse than this. But it is a continuous, or it's a C infinity curve, and it can never hit 0. So it is strictly between 0 and 1. So that means that you can define the smallest distance to 0. So let this distance be delta of beta. So you can define a smallest, because when you hit 0, it's when this kind of fractal thing starts to happen. So he looks at this minimal distance, and he can actually follow this to the very limit and show that delta of beta is equal to some constant which you can compute if you want. So some constant times 1 minus beta plus small little ordo 1 minus beta, as beta tends to 1 minus. So it means that the minimal distance, if this is beta, this is delta of beta, it means that the minimal distance goes linearly to 0. And this has been observed. I think the first one who did this was Rafael de la Llave and Alex Arro. So they did some numerical papers in kind of how invariant tora is the normal hyperbolicity of them, how they disappear. And they also find that this is kind of general, that you have this linear, that the minimal distance tends to 0 linearly. But you have to kind of remember that they are very fractal. I mean, they are very wrinkled, these curves. And he can also show that let me put it here, that if you look at the derivative, so let's take the C0 norm of the theta of psi beta. So if we look at the C0 norm of the derivative of this, so the maximal derivative of this curve, it's 1 minus beta to the 1/2 and another constant 1 minus beta to the 1/2. So you see that this goes to infinity, but you can really trace how the maximal derivative of this goes to infinity. And then at when beta is equal to 1, you have this attractor. So, and these scaling limits that the minimal distance goes linearly, that you have this square root of the derivative, it's been found numerically in many other models. But it's really difficult to prove that they are like this. But at least in this model, we can really give rigorous proofs for this. Then there also seems to be some kind of asymptotics in the Lyapunov exponent. But we don't have good enough estimates on the Lyapunov exponent to really trace this, what is asymptotic of it. It seems to be like a square root, but we cannot trace it. So this was one of the models, and I wanted to say that you can get these strange non-chaotic attractors in this model. Of course, you could get much more probably. And that you have these kind of scaling limits which exist. There are some power laws. So let me switch to to the Schrödinger co-cycle now and show that there are similar things going on there. Let me see. So now come number 2. So it's a quasi-periodic Schrödinger co-cycle. So now we have a map F from, again, the circle, but now cross R2 to itself, which looks like theta and x. Now x is a vector. Theta plus omega a theta x, where this a of theta, I always write it like this, minus 1 f of theta minus e. And this map f from T to R is continuous at least. So we have these maps, and we want to understand the dynamics of them. So we have E here is this parameter. I always like to have the matrix like this because I think it's natural to have un plus 1 instead of un plus 1 un, but it's a matter of taste. So this is in SL2R. And then we'll want to look at the iterates of this map, so we let AN be the time evolution, so, or the monodromy matrix. And then you define it similarly if n is negative, and then it's an identity if n is 0. So then we know that the nth iterate of theta and x is just theta plus n omega a n theta x. And then we introduce the Lyapunov exponent, or the maximal Lyapunov exponent. I call it for gamma. So we just take the limit n tends to infinity. Yep. So here I stress that the E. So E will be our parameter. So F should be fixed, omega should be fixed, and then we look at how the dynamics change with the energy. And that is the analog of this beta in this model, that we have a parameter which we play with. So now there are some different dynamics of this map. So let us divide the parameter space a little bit. So let UH, uniformly hyperbolic, be the set of parameters E such that Fe is uniformly hyperbolic. And then I let sigma be the complement. It's sometimes called the Zucker-Cell spectrum. And then I say that the non-uniformly hyperbolic, it means that you take an energy which lies in sigma, and that the Lyapunov exponent is positive. It's a non-uniform hyperbolic. So first we have uniform hyperbolic, then we have the complement, and then we have this non-uniform hyperbolic. And then we know that to this co-cycle is associated a rotation number, which measures the average rotations in the x direction, or in the fiber. So we have the fiber rotation number of this map Fe. So this was by Johnson, Moser, and Michel Herman has a definition of this. But it means that there is a function rho of E, which is monotone. It is continuous and monotone, and it goes between 0 and 1/2. And if this is the E, well, it is some monotone thing going from 0 to 1/2. And it measures kind of how a vector in average rotates around, as we iterate there. And then it's the famous gap labeling. So we have the gap labeling. Which says the following, that if I take a parameter for which the co-cycle is uniformly hyperbolic, then I know that 2 times the rotation number has to be equal to the integer part of k times omega, where k is an integer. So the rotation number has to be of that form, k times omega and the fractional part. So for example, if you have a gap where you are uniformly hyperbolic, the rotation number is constant, because you can't change that. And then, so that is the rotation number. Let me see. So now I introduce a one-dimensional system. So to kind of, in this first model we had a one-dimensional system, but instead of looking at this as a map from T cross R2, let us see how it acts on the projective space. So instead of looking at vectors, we look at just the directions of the vector. We could take the angles as well. So we have the projective co-cycle. So we say that this map F, it induces in the natural way a map phi from T cross P, and I'm used to think of this as R union the infinity, but you can think of it as a circle or well, it is a circle, but I normally use these coordinates. So you think of an object in this as 1R. And then the map is the following. So what it does is the following. So you take a theta and you take an R, and then you map it to theta plus omega a theta, and then it acts on this R, and then you get a map which is just phi of theta R is theta plus omega f of theta minus e minus 1 over r. So this is how the map F acts on the projective space. So you take R, which you think of as a vector like that, you get a new vector 1 and this. And let us see what is the picture when you are uniformly hyperbolic and when you are non-uniformly hyperbolic. So if the parameter E belongs to the parameter for which you are uniformly hyperbolic, then let me try to draw a, so this in the base we have T, in the fiber we have P, so this is a 2 torus, of course. But then we know that for every theta, so we have this, for every theta there are 2 subspaces, one in which the vectors grow exponentially fast forward and decay backward, and vice versa. So it means that you have 2 curves. Now they can of course wind around some numbers depending on the rotation numbers. But so you see, for each theta you have 2 directions. One is the one when you iterate forward you contract in that direction, and one is expanding and vice versa backward. That is to be uniformly hyperbolic, that these are continuous as functions of theta. Does it make sense, this? So it's being uniformly hyperbolic. And then you see that the dynamics, I mean, either forward you're attracted to this, and backward you're attracted to that one. And you have exactly 2 invariant probability measure, one sitting on this graph and the other one sitting on that graph. Now, what happens when we become non-uniformly hyperbolic? It means that we have assumed that the Liouville parameter is positive, but you don't have this uniform structure. So if E belongs to non-uniformly hyperbolic, then by the Oscillides theorem we know that for almost any theta there are these directions, but now they can come arbitrarily close. So then we have some, so we have one like that and then the other one. So they are very kind of fractal. So still for any, for almost any theta you have 2 points, one sitting in that. So it's a projectivization of the 2 directions. And in this case, this map phi, the projective cocycle, has a unique minimal set M in T cross P. And to be minimal, it means that you have a closed set in which every orbit is dense. So minimal, so you take any point and you iterate it and it's dense. And it means that it has a unique, there is one set here in which the dynamics is dense. And this is some kind of attractor. So this should be kind of the analog from what I did in the previous model, that as you change the energy parameter E, it undergoes some kind of bifurcation. So you go from these nice continuous curves to this fractal thing. So this was proved by Johnson and Hermann separately. That you have this. As soon as you are non-uniform hyperbolic, you have these minimal sets. So you can think that you have these 2 invariant graphs, and on each there's theta probability measure, but the support of the 2 measures are the same. So let me connect this to the Schrödinger operator. This was the Schrödinger cocycle, the projective cocycle, and now the Schrödinger operator. No, sorry, I will take another one. So the Schrödinger operator, well, I define it, so it's h theta from little l to z to itself, just acting as h theta u of n is minus un plus 1 plus un minus 1 plus f of theta plus n minus 1 omega un. And then we see for each phase theta, we get an operator. So the f is the same as in the cocycle. And then we have that the spectrum of this operator, sigma h, is independent of theta, since I assume that f is continuous. And now this time evolution a n theta, it is just a fundamental solution of this equation, of the Schrödinger equation, h theta u is equal to e u. So this is a fundamental solution. And then there is a fact due to Russell-Johnson, that the spectrum of this operator is exactly the same as the Zucker-Sells spectrum. So it's exactly the values of E for which the cocycle is not uniformly hyperbolic. So that is the dynamic correspondence between like uniform hyperbolic and being in the resolvent set. Okay, so now I wanted to present some results. So now we have the key. So this is one of the key objects and these sets and the Lyapunov exponent. So now we have to go to our setting here. So our setting. So we want to have the Lyapunov exponent positive so that we have parameters for which this is non-uniformly hyperbolic. So in some sense, and it's easiest if f is very large, because then a big matrices. So we need large f. So we take them like this. F of theta is lambda f naught of theta, where lambda is very big and f naught is some given function. And then we take f naught to be cosine-like, meaning that assume that this f naught from t to r, that it is C2 and has exactly two non-degenerate critical points. So it looks something like this. So two critical points. So cosine is an example of this. And then we assume that omega is Diophantine. And this model has been studied by several people. So let me summarize it in one theorem. So this is by Fröhlich, Spencer, and Wittberg, and independently Sinai. And they looked at the Schrödinger operator under these assumptions. So they say that for all lambda sufficiently large, this Schrödinger operator has a pure point spectrum for almost every phase theta, and then this by the Koutani theory, this implies that the Lyapunov exponent is positive for almost every parameter E. So it has a pure point spectrum, and Sinai, he can also describe the geometry of the spectrum, so he proves that the spectrum is a Cantor set. So if this is the E, we have this Cantor set, which is the spectrum, which is for us the parameters for which the map is not uniformly hyperbolic. So let me state my theorem in the exactly same setting. We can take it. Here. So here comes the theorem. It just appeared in April number of Annales Henri Poincaré. So for all lambda sufficiently large, so the size, it always depends on the F naught and the Diophantine properties of omega. We have the following. First, the Lyapunov exponent, gamma, it's in the size of log lambda for all values of E. And the second thing is that, so now we know that since the spectrum is non-empty, that there are parameter values for which we are non-uniformly hyperbolic. It means that we have these kinds of strange sets, and then you can ask, what do they look like? And the second is that the projective cocycle is minimal, and being minimal means that this minimal set is a whole space. It means that any point is dense, the iteration of any point is dense. It is if and only if E belongs to, let me maybe use this notation, the spectrum, let me take, it belongs to the spectrum minus edges of gaps. So you see, we have this set which is a Cantor set. It means if you are not on one of the gap edges, you immediately have that this set is a whole space. It means that I think this result is new even for the cosine. But the directions of this, they are everywhere. And you have this exact classification that as long as you're not on the gap, on the edge of the gap, you are minimal. And then a third thing which just pops out from the proof is that if E belongs to the set of edges of open gaps, I should say edges of open gaps here. Then this is an eigenvalue for some phase for the Schrödinger operator. Then there exists a theta and an x in R2, which is not 0, such that an theta for this E of x tends to 0 exponentially fast as n tends to plus minus infinity. So we can find a solution which decays exponentially fast forward and backward. So it's an eigenvalue of the operator for some phase. So, I mean, for most theta, you should expect that it is, for some phases, it is an eigenvalue. But it's not true that for any E that you can always find a theta which is an eigenvalue. But at least you can pinpoint these ones. So there is a result by Soshnikov who proved that the lowest energy is always an eigenvalue. But now you get it, that for any gap edge, you're an eigenvalue. So let me say some words about the behavior at the gap edges. Yeah, I should also say that this has recently also been proved by Wang and Zhang. And I think that Jackson-Chan's machinery should also work here. Maybe. He has results in this direction. So let us now focus on the gap edges to kind of connect with these attractors in the first part. And I just wanted to say that. So at a gap edge, we are still in the spectrum. So we have this strange minimal set, but it's not the whole space. So what does it look like? And in principle, I think one could analyze for any gap edge, but I've only done it for the lowest energy. So at E equal to the minimum of that. So now we focus on the lowest. The lowest energy. And then, in fact, if we look in the projective space, so let's say that this is theta, then one can show that the rotation number is 0 and that these two directions given by the Oscillidis theorem, they will always be between 0 and infinity. So they don't wind around. So you really have the graph of two you can think of it as a graph of two measurable functions. So you have, well, it's difficult to draw them, but and then they are somehow fractal here. So let me call the one is L plus, is the upper one, and the other one is L minus. Sorry. So this, for almost any size, these are the two Oscillidis directions. And you can show that the direction really lies in the upper part of this. Goes around, but so it's L plus and L minus. And you can actually show that, so it was the theorem I proved a while ago, that this minimal set M is what you could say filled in. That it looks the following way. So M, it is really of this form, so that it's theta in T and L minus of theta is more equal to. So it's really, if you take, so for almost any theta, these are different, but this result shows that anywhere between that you have like into. But still there are points where you only have 1 point. So it's some kind of filled-in set. And I think you could do the same with analysis we have to show at each gap edge. But now they can wind around, but the structure is like this, and as soon as you leave the gaps, it blows up and becomes everything. So there can, for example, not be any kind of, you could in principle imagine some kind of Cantor structure here, but in this case it does not exist, and I think you could do it for any of these gap edges. And so this is, you can say, on the boundary of becoming non-uniformly hyperbolic. Here you are non-uniformly hyperbolic. If you change E just as tiny, you get something uniformly hyperbolic. And you could look at the asymptotics here. How do they form? And this is something I did with my wife a while ago, with Maria Saprikina. We had a little bit different model, but it's the same proof. It's the following. That so this is a theorem Saprikina. So again, so now we look at energies which are smaller than the lowest value in the spectrum. And then we have two continuous curves. So this is L plus of E and L minus of E. So you have two continuous, and as we reach, let me call this for E naught, this is the smallest. And then as we reach E naught, they somehow collide and you get this strange thing. Yes?
On the vertical line, you have actually the projective.
It is a projective, so it is a circle.
So
but actually in this,
therefore, there is no order. What you decide is between and what outside.
yeah. So I say that this is zero. If I think of projective space as R, this is R0, and then I think that you go to infinity and then you come back. And then I say that in this case, when you are at the lowest energy, they don't wind around, so you really have an order. That is order. Thank you. So now you can define a distance between these curves. Well, you take either in that direction or in that. You take the minimal distance between them on the circle, and we call it for delta V. And here again, you could prove that this delta V is some constant times E naught minus E plus some small error E naught minus E as E tends to E naught minus. So again, one sees this kind of universal scaling, that you go linearly, the distance goes linearly. We have not checked what happens with the derivatives in this model. So they will wrinkle up and then you get it. But I think this is, so that was what I kind of wanted to focus on this talk, that there seem to be lots of general things for much wider models than just the Schrödinger co-cycles. That you have like this kind of how these attractors appear. That, I mean, in quasi-periodically forced systems, we often see these attractors. And this has come somehow, there seem to be scaling limits in how they are born and so on. And this is also good when you do numerical experiments, because then you know how much you can change the parameter before you get into non-uniform hyperbolic. If you know the distance and you know, okay, I can make a further perturbation like that before it breaks. So it's good to know this for if it's very general, that you have results. So I think there is lots of to do also outside the Schrödinger co-cycle. There are many other systems, and there are things like dynamical objects which are quite robust and which you actually can analyze. So I think I finished that. So thank you for your attention.
Do you also know something for the scaling of how the Lyapunov exponent
No,
changes?
it's good that you take it. We think it goes like square root, but we cannot.
Okay, so I think there's some numerical work also from De La Llave, right? That
Yeah.
looks like square root.
Yeah, because when you look at, if you plot Lyapunov exponents for Schrödinger co-cycles, you always see, I mean, you always see this picture that when you have gaps, the Lyapunov goes something like this. Yeah? And it goes down like square root. But we don't have good enough estimates on the Lyapunov exponents. We just make sure that it's bigger than something, or we can't. We don't have such a fine estimate so that we can see how it changes with you.
Speaking of the minimal sets you described, from the point of view of measure theory, can you tell anything about distribution, either globally or maybe just in local times?
You mean how much time it spends? I mean,
Yeah.
there are two, like,
In between, I mean,
in between it spends very little time.
But still, if you take local times,
Yes.
can you say something about that? About the limit in distribution and its regularity with respect to the day?
I have not analyzed, but it should be possible to check it. It should be.
So it follows from your.
Yes, it follows because you have total control on the orbit.
Do you expect the second part of your theorem to be universal in some sense?
Well, that is what I... Actually, the starting point for more or less this project was that Russell Johnson asked me a question. So, can you produce a minimal... Well, so assume that the rotation number is irrational with respect to omega. Can you construct a minimal set which is not the whole space? I mean, can you get something else? Because very, very intuitive, you can see if the fiber rotation number is irrational with respect to base, somehow you should get that it's minimal. But I cannot construct such a example, and instead I got the theorem that there are no.
So there is no counterexample.
There are no known counterexamples, at least what I know of. So either you have to go into to Liouvillean frequencies. Russell Johnson has counterexample, but then you have almost periodic base.
I see.
But for the quasi-periodic, we don't know.
So, okay, so at least for one frequency rotation, there
Yeah.
is no counter.
No.
Are there any other questions? Okay, now let's thank the speaker again. Thank you very much.